So I want to continue our discussion from last time. If you haven't sent your attendance, please send it text to this number. First, last name, EET 131. So in the last class, we talked about the Bohr model of the atom, and I want to continue that discussion. This time I want to show an atom. Here's the nucleus. I'm not going to say how many protons the nucleus consists of. We'll just kind of draw a general nucleus. And I'm going to draw these orbits. I drew the orbit last time, and I drew a single orbit. And that single orbit is true only for the hydrogen atom and the helium atom. All other atoms have more than one path that electrons take as they revolve around the nucleus. So I'm going to draw a couple here. And again, remember, I want to remind you, I'm trying to draw something that's three-dimensional on the two-dimensional surface. So these are really spheres, even though I'm drawing circles.
Hey, Riley, could you mute your mic?
What did you say?
Could you mute your mic?
Oh, okay. Oh,
Thank you.
Sorry.
Just pull it up as the big screen.
All right. So I have a model of an atom, and again, with these dotted lines that represent the trajectory or the path that the electrons take as they revolve around the centerpiece, which is the nucleus. Now, there's names. These are called shells. They're also called orbits. They're also called energy levels. So I'm trying to indicate that the electron follows certain paths, and they exist at certain distances, certain fixed distances from the nucleus. And so these orbits or shells, we like to name them. And usually what we do is we name them with letters of the alphabet. If I name them, I can talk about them. So the one right away, right closest to the nucleus, we call that the K orbit or the K shell. So we name them in alphabetical order starting with K. So this first orbit is the K shell. Then we have the L shell, and then M, and then N. So I can label each orbit or each path, and in addition to a alpha number or letter, there's also a number associated with each orbit or shell. So K has what we call a shell number. The shell number, K has shell number 1. So K is equal to 1. And all that means is it's the first orbit away from the nucleus. And then you just count outward. L would have a shell number of 2. N will have a shell number of 3. And N would have a shell number of 4. So each orbit or shell has a letter to name it, and each orbit or shell has a shell number. And again, we just count out from the nucleus outward to get the correct shell number. Now, why is this important? Well, it turns out that each shell here has a maximum capacity of electrons that it can hold. Think of a shell as a bucket of different sizes. The further you go out, the bigger the bucket. So the K shell can hold a certain number of electrons. The L shell can hold more than K. The M shell can hold more than L. And the N is the biggest bucket. It can hold the most electrons of all. And the question is, okay, what's the maximum amount of electrons each shell can hold? That's called the shell capacity. Shell capacity. And you can actually calculate the shell capacity. It's pretty simple. Let me make a chart here. I want to make a table that consists of the shell, the shell number. We'll just call the shell number. We'll use a lowercase n for the shell number. and then the shell capacity. So you copy this down. I have shell, we start with K, L, M, N. So those are my 4 shells. Now that lowercase n represents the shell number. And that's the number 1, 2, 3, or 4 in the diagram. And so K has a shell number of 1, L has a shell number of 2, M is 3, and N is shell number 4. What we're interested in, though, is the shell capacity. The shell capacity is the maximum number of electrons each shell can hold. And so that's this last column. That's the shell capacity. I'm not going to write it on the board, but you make sure you write in your notes. What I mean by shell capacity, that's the maximum number of electrons each shell can hold. So how would you figure that out? Well, there's a handy little equation that allows you to calculate the shell capacity for each orbit. Shell capacity is equal to 2n squared, where that n right there is the shell number. That n is one of these numbers. So I can use that to calculate the shell capacity for the K shell. Let's do that. So for the K shell, the shell capacity would be 2. N for the K shell is a 1, so I got 1 squared. 1 squared is a 1, and 2 times 1 is a 2. So the shell capacity for the K shell is 2. The K shell can hold a maximum of 2 electrons. What about L? Well, the shell number for L is 2. 2 squared is 4, and 2 times 4 is 8. L can hold up to 8 electrons. I can keep doing that. M is 3. 3 squared is not 6. 3 squared is 9. 9 times 2 is 18. M can hold up to 18. And last but not least, N is 4. 4 squared is 16. And 2 times 16 is 32. So now, if I know the atomic number of an atom, we can do certain things with it, and I'll just show you here in a second. But let me show you how this works. Suppose I have an atom that has 3 electrons in it. So here are the 3 electrons. And I want to place those 3 electrons in that atom. I can't just put them anywhere. I got to put the electrons in the first orbit, and if I have any left over, they go into the outer orbits. So what I'm saying is, K can hold a maximum of 2. So 2 of these electrons I have to put in the K shell. I always start with K. So I put 1 here and 1 here. What about that third one? Well, that third one goes to the next level up. Since K shell is full, I got to put that third electron in the L shell. So now I've distributed all those electrons to the atom, and my atom is complete. Now notice I didn't have any to put in M. I didn't have any electrons to put in N because I got to fill up L first. I can add 7 more electrons to L before it's full. The last shell that has electrons in it, in this case the L shell, that last shell is called the valence shell. That's important, the valence shell. So for this example I showed you, the valence shell is L. That's valence. Valence means the outermost shell. And any electron in that valence shell, those electrons are called valence electrons. And valence electrons are important because they're going to help us identify what kind of electrical material we have. So, one of the things I would expect you guys to be able to do is to take a bunch of electrons and distribute them to an atom like this and get that part right. You got to know either this table, you can memorize the table, or much easier is to understand this equation. Then I can use this equation to populate the shell capacity, and I can distribute the electrons that way. So let me, anybody have any questions over what I just did here? Okay, so well, let me move away from this. So far we started in the last class, and I continue to this class, giving you a kind of a view or picture of the atom. And then we talked about two different ways to represent an atom. One would be the quantum model. The other is the Bohr model, which I'm showing here on the board. We said that the quantum model was overkill. We went in and we talked about some specifics that relate to the planetary model or the Bohr model of the atom. Now, I want to talk about categories of materials, categories of electrical materials, and there's three of them. When I have what I'm referring to as electrical material, that material can be a conductor, when I say a conductor, I mean a conductor of electricity, or it can be a non-conductor. I have conductors and I have non-conductors. If something conducts electricity, we call it a conductor. If it's a non-conductor, we call it an insulator. You might think to yourself, well, hold on, you said there were three. Well, there really is. There's one more. I'm going to abbreviate it here. You can write it out. It's called a semiconductor. I don't have a lot of room here. Semiconductor. So in the electrical world, there's three classes of materials. There's conductors, there's semiconductors, and there's insulators. So, what is a conductor? Who can tell me what is a conductor?
Something that can transfer energy.
Okay. How about this? Something that can transfer
Current.
electrons, right? Now, he's actually right, transfer energy, because electrons carry energy, but I don't want to go that far. A conductor allows electricity to flow through it with relative ease. A conductor allows electrical flow through it with relative ease. And most people know that metals pretty much are conductors. Most conductors are metal. So whether it's silver, that's a really good conductor. A conductor that's used a lot of metal is copper. Most wire in your house is copper. But practically all the metals are pretty good conductors. Whereas on the other end, I have insulators. So give me an example of an insulator. Any material that you think is an insulator.
Rubber.
Say it again.
Rubber.
Rubber's a really, really good insulator. Plastic is an insulator. Wood is an insulator. Vinyl is an insulator. Glass is an insulator. There's a lot of materials that won't conduct electricity easily. Let me say this. All materials conduct electricity. All materials, the question is, how well do they conduct? If it's really hard for current to go through a material, we say that it's an insulator. If it's relatively easy for current to flow through a material, we say it is a conductor. Okay, well, what about in the middle here, semiconductors? Well, is this what you think? A semiconductor is kind of right in between. It's not a good conductor or a good insulator. It's kind of just stuck right there in the middle. How about water? Is water a good conductor or is water a bad conductor? H2O, water.
A good
It's a
one.
bad conductor.
Okay, I got both answers. It's like Congress. I got two different answers. Somebody said a good conductor. Somebody said a bad conductor. Well, most people think water is a good conductor, but in reality, water is a terrible conductor. It's actually a bad conductor. What makes water a good conductor would be impurities in the water. So water, if you took distilled water, you can do this example when you get your own meter. When you get your meter, you can take a glass of distilled or boiled water and you can put your own meter in it and measure the resistance of the water. It's going to have a high resistance. But if you put some kind of impurity in it, like maybe salt or other impurities, and you stir it up, you'll see the resistance drop. So often people, when there's electricity and water, electricity and water don't mix, but it's not the water per se, it's the impurities in the water. So this is probably a bad thing to say. You know how on TV where they got maybe they got the girlfriend in the bathtub and the boyfriend wants to kill her, so there's a radio in the bathroom, so he pushes over in the water and electrocutes her. That doesn't really, well, it will work, but if you want to kill your girlfriend, put some Epsom salt in the water, mix it up, and then put the radio in and electrocute her. Now, don't do that for real. I'm just kidding, but it's true.
Oh, okay.
I see so you guys have some ideas, Robert. So, is it possible to determine if a material is going to be a good conductor, insulator, or semiconductor? And the answer to that question is yes. You can do it if you know the number of valence electrons. So, it turns out that good conductors will have 1, 2, or 3 electrons in the outermost shell. Those are called valence electrons. So if I start with a neutral atom and I count 3 electrons in the outermost shell, or 2 electrons in the outermost shell, or 1 electron in the outermost shell, then that material is going to be a conductor. If I have 5, 6, 7, or 8 electrons in the outermost shell, then that material is going to be an insulator. Now this is actually pretty interesting because it turns out that the closer I get to 8, the better insulator I have. Let me say something about insulators and conductors. We know a conductor allows electricity to flow through it with relative ease. And we understand that an insulator doesn't like for current to flow through it. But in an application, we usually use the two together. Typically, they're used together. If you think about it, when you take a conductor like the cord, maybe you got a lamp in your room right now, your computer, you got something plugged into the wall. When you plug those blades into the plug receptacle, you can see the conductors that go into the plug. You can't handle those with your bare hands, so they're wrapped in rubber or plastic or vinyl. They're wrapped in an insulator. And the insulator does 2 things. It allows you to handle the wire, and it also keeps the 2 wires. There's usually 2 wires in the cord with a little bit of insulation between them, and insulator between them. It keeps those 2 wires separate. So usually we use the 2 together. It turns out that the closer I get to 8 valence electrons, the better insulator I have. Now we don't know why that's the case. We know that when I have an atom that has 8 valence electrons, we say that that atom is stable. It's chemically stable, which means it won't react with other elements. But more important for us, it's electrically stable, which means if I want to remove an electron from an electrically stable atom, it takes a lot of energy to pull that electron away. It doesn't want to give that electron up easily. And those are the best insulators. So we don't know what's special about the number 8, having 8 valence electrons, so scientists call this the magic number. Magic number. So if for some reason you want a really, really, really good insulator, try to find one that has 8 electrons in the outermost shell. Those are the best insulators. And then, of course, you might think, okay, well, right in between 3 and 5 is the number 4. So any atom or any element that has atoms that have 4 valence electrons, that particular element will be a semiconductor. So one of the things you got to be able to do for me in this class is, given a material, you got to be able to tell me, is that material a conductor? Is that material an insulator? Or is that material a semiconductor? How would you do that? So I might say, let's go with something we know. Let's go with an answer we already know. And we already know that most wires in your house made of copper. Copper is not the best conductor, but it's a good conductor. One of the best conductors is like silver or maybe gold, but those are expensive and there's reasons why we use copper. Copper has a high conductivity, and it also, compared to silver and gold, is relatively inexpensive, and then we can bend it. We can do a whole bunch of stuff with copper. So let's say I have copper. and I want to know, is copper a conductor, is copper a semiconductor, or is copper an insulator? Now we know it's a conductor, but let's say you didn't know. Maybe this is element X instead of copper. We're going to go with something we know, copper. So how would you determine that? Well, some of you would just Google it, but that's not education. Anybody can Google. How would you start with an element and figure out, knowing this information right here, if this is going to be a conductor, insulator, or semiconductor? So what you would do is you would start with the periodic table. And I think I talked about the periodic table in the other class. I hope I did. But given the periodic table, you would identify the element of interest. So if you look here, where's copper? Which one is copper? Do you see it?
27.
Okay, Caleb said, not 27, Caleb said the element is Cu, and it's this one right here. It's number 29. And what do we say that number 29 represents? What is the number above the chemical symbol? What does that represent?
The amount of electrons?
That's called the atomic number, and it represents the amount of, not electrons, the amount of what?
Protons.
Protons. The atomic number represents the number of protons. So Cu, copper, has 29 protons. But remember what we said the other day. In this class, we always assume we start with the neutral atom. If I start with a neutral atom, if I know the number of protons, then I also know the number of electrons. So copper, I look it up. I see that copper has 29 protons. I'm going to assume I start with a neutral atom of copper, which means I have the same number of electrons and protons. If I have 29 protons, then copper is going to have a neutral atom of copper. It's going to have 29 electrons. So that's the first step in solving the problem. Get your periodic table, find the element of interest, figure out the number of protons, assume you start with a neutral atom. In that case, the number of protons and the number of electrons will be equal. So now we know we have in copper 29 electrons. So what I'm going to do is I'm just going to group those electrons. I'm just going to write them on the board as little dots. I need 29 electrons. I'm going to show them as dots. So 29 dots. I like to group them in tens because they're easier to count. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there they are. I got 29 dots that represent the 29 electrons in copper. Now what I want to do is distribute these electrons to the atom over here. Let's get rid of these. I want to distribute the 29 electrons to the atom, but you got to remember what we said about shell capacity. The K shell has a shell capacity of 2, L has a shell capacity of 8, M has a shell capacity of 18, and N has a shell capacity of 32. And so as we distribute these electrons to the shells, I got to start with the K shell. I start with the one closest to the nucleus. So I'm going to assign each of these to a shell, starting with K. So K can hold a maximum of 2. So these two right here are in the K shell. L can hold a maximum of 8. So the next 8 are in the L shell. M can hold 18. So I have 19 left. So I take 18 of the 19. I can see that these are in the M shell, which means that this one right here, that's in the outermost shell. That's in the N shell, and it's I have one electron out there. That makes that N shell, N is in Nancy, it makes that N shell the last shell or the valence shell, which means the electron in the valence shell That's the number of valence electrons. Copper has 1 valence electron, and if a material has 1 valence electron, 2 valence electrons, or 3, that makes it a conductor. So we already knew it, but I want to show you using that shell capacity formula or these numbers, and if you know the atomic number of the material in question, you can figure out where it falls as a conductor, semiconductor, or insulator. Pretty easy to do. So I think on the practice sheet, there's a practice sheet somewhere on the blackboard. This is like one of the first problems on there. Okay? All right, so this is all nice and dandy, but we still haven't gotten to the question, what is voltage, what is current, what is resistance? And we got a ways to go before we get to that. So does anybody have any questions over anything I went over so far? We talked about the atom. I talked about categories of materials, these categories, conductor, semiconductor, insulator, and how you use the idea of shell capacity to figure out if a material is a conductor, semiconductor, or insulator. Anybody have any questions or comments? All right, well, let's look at the topic sheet and see where we are. I'm looking at the topic sheet. Roman numeral number 1, talk about atoms, the Bohr model, energy levels, valence shells, ionization. So we talked about that. Categories of material, there are conductors, semiconductors, insulators, 3 classes. We know and gave definitions for each of those. And so we talked about that. And then Roman numeral number 3 talks about shell capacity. They give you the formula for shell capacity. And using shell capacity, you can figure out the maximum number of electrons I can put in each shell. And shell capacity, along with this table right here, if you know how to distribute those electrons, you can tell which of the 3 classes of materials you have if you distribute it the right way by counting the number of valence electrons. So that's what we talked about so far. Now, number 4 is kind of the pivotal part of this discussion, because number 4 kind of sets us up so we can actually understand what voltage is. So I don't know if we'll get to it today. I'm going to do my best, but I want to spend time there with number 4. So number 4, if you look at the sheet, is called electrostatics. Look at number 4, and if you jump down to number 4, 5, 6, they have the term electrodynamics. So in physics, there's this term electrostatics and electrodynamics. If something is static, what does that mean? What does that mean if something is static as opposed to dynamic?
Something doesn't move.
Yeah. If something is static, it's not moving. If something is dynamic, it's moving. And so we're dealing with electrostatics. Electro kind of makes you think about charge. So we're talking about now charge that does not move. That's electrostatics. What we want to get to is charge that moves. That's electrodynamics. And all that is current flow. So that's what we aim to get to. So I want to talk about electrostatics. And I want to talk about a term that I've already used several times in this discussion. And that term is charge. Let's examine that term. Charge. Who can tell me what is the difference in English, in the English language, what's the difference between a verb and a noun?
Noun describes something. A verb is an action.
Okay. A noun describes something or names something, and the verb is an action. So usually you can classify a word as a verb or a noun, but in English it's kind of weird because sometimes I can use the same word as a verb or I can use the same word as a noun. For example, Google. Well, what is Google? Well, Google describes something or names something. We all know that Google is a search engine, It's the name of a search engine. Therefore, the term Google is a noun. But I can also use Google as a verb. I can say, go Google something, right? I can use work, the term work, W-O-R-K. Work could be describe a place that you go. A work could be something that you do. I can use work as the term work as a verb or a noun. Well, charge is exactly the same. I can use it exactly the same way. I can talk about charge as a verb, or I can talk about charge as a noun. And when in here, most of the time we talk about charge, we mean charge as a verb, or at least in the description or discussion I'm about to enter into with you, I'm talking about charge as a verb, not a noun. What do I mean by a noun? Well, charge as a noun is like this. I know I have protons, and I know I have electrons. And the only difference between the two, other than the physical size, you know, the proton is way bigger. But the only observable difference is that the proton is going to have positive charge, and the electron is going to have negative charge. So charge, in this sense, is a noun, is something possessed by the proton or possessed by the electron. That's using the term charge as a noun. That's not what I'm talking about right now. I want to talk about charge as a verb. What does it mean to charge an object? And I'm using it as a verb. So let me show you what I mean. So I'm going to go back to the atom. So we have an atom, and let's say the atom has an atomic number of 3. So there's 3 protons in the nucleus. It's a neutral atom. So if it's a neutral atom, then I have 3 electrons orbiting that nucleus. So one of those would be, we now know, in the K shell. I'll have another one in the K shell, and that last one will be in the L shell. So if I have 3 electrons, I got 1 electron right here. But that K shell has a shell capacity of 2, so the other one is maybe over here. And then we'll put the third one out there. So now, I have a neutral atom. And what I'm going to do is, I'm going to put this imaginary box around it. I got this imaginary box around that atom. How much charge is in the box? And what I'm asking is, what's the net charge in the box? I have 3 positive charges in the box. And I have 1, 2, 3 negative charges in the box. So my net charge, my total charge in the box is 0. A net charge of 0 doesn't mean I don't have things in the box that has charge. It just means they add up to 0. So the net charge is 0. Now what I want to do is I want to charge. Now when you charge an object, we got to talk about the area around the object. So I want to charge this area around the object. I want to charge it. So here's how I'm going to do it. See this electron? I'm going to take that electron off the atom. I'm going to put it somewhere else in the universe. Stick it over here. Now, I can't remember, guys, in the last class, did we talk about the conservation of energy principle? Did we talk about conservation laws or not? Remind me. Does that ring a bell?
I don't think so.
Okay. Well, you all know it already. Finish this statement. Energy is neither created or what?
Destroyed.
Destroyed. Everybody knows that. Energy cannot be created or destroyed. You can only change it from one type to another. That's called the conservation of energy principle. It's the most basic law in physics. That's law number 1. Often people can state that, but people don't understand or maybe may not realize that energy is not the only thing that's conserved. There's many laws or conservation laws that apply to other quantities. For example, mass is conserved. In physics, momentum is conserved. And in this case, charge is conserved. What does it mean to say charge is conserved? What it means is if I have positive and negative charge, I can't make it disappear. All I can do is move it around. So notice that electron that was here, I moved it over here, but it's still in the universe somewhere. It still exists. I just moved it away from this atom. I moved it out of this region that I have in the square. Now when I go in here and I say, all right, what's the total charge in the box? You count. You say I got 3 positive charges. I only have 2 negative charges. I now have a charge in this box of +1. I just now charged the region in that box. Let me charge it another way. Let's say I go back to the original atom. So now I have 0 charge in there because I got 3 positive, I got 3 negative. The net charge in the box again is 0, no charge. Now what I'm going to do is go out somewhere else in the universe. I'm going to steal another electron from another atom. I'm going to put that other electron in the box. So here it is. Now when I count the total number of positive charges in the box, I got 3 positive charges. But I have 1, 2, 3, 4. I got 4 negative charges. When I add these up, I get a charge of -1. I now have charged the region in the box with a charge of -1. The first time I charged it with a charge of +1. In both cases, whether I'm charging the thing, the object, the atom, whether I'm charging it to be negative or positive, in both cases, what did I have to do? What did I have to do?
Remove or add.
Yeah.
I had to what?
Remove or add an electron.
I had to remove, or add an electron. Write that down, because when I talk about charging something, when you talk about charging something, when most people on the planet talk about charging something, they don't mean charge as a noun. They mean charge like this. When you say I'm going to charge my cell phone, what are you saying? You're going to take electrons and move them from the charger to the cell phone. I left my headlights on, my battery's dead. I need to jump. I need to charge my battery. You're going to take electrons from the good battery, send those over to the bad battery. Anytime in this class you use the term charge, this is what you mean. In order for anything to charge, in order for any charge to take place, there must be a transfer of electrons from one place to another. Write that down. In order for charging, I don't care if you're charging your cell phone, your computer, a battery, if you're using the word charge, what you're doing is some kind of way you're moving electrons from one object or thing or place to another. That's what we mean by charge. So, on the one hand, charge could mean something that it's an attribute that something can have or contain. I can have something that has positive charge. I can have something that has negative charge. So we could talk about that. But 99 times out of 100, when you use that word charge, this is what you mean. Electrons are moving some kind of way. If anything's charging, there must be a transfer of electrons either to an object or from an object. And this idea of charge is really important. And in science and engineering, when something is important, we give it a symbol or we give it a name, right? You know some of these, like this is important, 3.14, so we give it this symbol. This is important, 300 million meters per second. That's the speed of light, so we give it a symbol. Well, charge is the same way. It's really, really important in engineering and science. So we give it a symbol, Q. Q. And Q stands for quantity of charge. Now, please don't just listen to me. Write this down. If I'm telling you to write it down, that means you're going to use it at certain points. Q stands for quantity of charge. Now, little notation. You know, to express a quantity, we need a number and a unit. Well, usually when we want to talk about the quantity, we give it a letter of the alphabet. So, for example, if I want to talk about voltage, I use the letter V to represent that idea of voltage. If I want to talk about current, I use the letter I to talk about to represent the idea of current. If I want to talk about resistance, I use the letter R to represent that concept of resistance. Well, that represents the number part. I also got a unit, and unfortunately I use letters to represent units too. I use letters of the alphabet to represent the quantity I'm talking about. For voltage, I use a V. For current, I use an I. For resistance, I use an R. And for charge, I use a Q. But I also use letters to represent the unit. For example, the unit of voltage is the volt. The unit of current is the amp. The unit of resistance is the ohm. And it can be confusing sometimes. If I put a letter on the board, am I talking about the letter that represents the number? Am I talking about the letter that represents the unit? So if I want to show something as a unit, what I'll do is I'll put brackets around it like this. So you know that's a unit. You know that's a unit. That's a unit. If you just see the letter without the bracket, well, that just means it represents some physical quantity like voltage or current or resistance. So what I'm saying here is Q, we use a Q to represent the quantity of charge, but the unit for charge, we use a capital C. Capital C. So that's a unit. And that C stands for coulomb. Coulombs. And that is a unit. Coulomb is a unit. Now, a coulomb is an amount of something. A coulomb is an amount of charge. So write that down. A coulomb is an amount of something. And the question is, what's the amount? How many, I don't know if anybody smokes. Anybody smokes cigarettes? How many cigarettes are in the pack?
20.
Okay. So one pack of cigarettes contains 20 cigarettes. A pack contains 20. 1 dozen eggs, that's 12 eggs. And 1 coulomb of charge contains 6.25 times 10 to the 18th electrons. A coulomb is an amount of something. A pack, that's the number of cigarettes, 20 of them. A dozen, that's the number of eggs, 12 of them. A coulomb, that's the number of electrons. We package the coulombs as 6.25 times 10 to the 18th electrons. So a coulomb is an amount of something. A coulomb is the number of electrons. 1 coulomb is equal to 6.25 times 10 to the 18th electrons. Now, I won't say you have to memorize that, but I would say that's a really good number to write down. Now, I don't know, guys, if you have this sheet out. That was on Blackboard. So if you have this, take it out. If not, I want you to copy down problem number 2, copy down problem number 3, and get your calculator out and try to work that out for me. If you don't have the sheet, just copy it off the screen. Problem number 2, problem number 3. We already did number 1, so we're going to do number 2 and 3. Copy it down if you don't have the sheet. Take your calculator out, and then work it. And then I want to show you how to work it together. All right, I want to borrow an idea from chemistry. If you guys have chemistry, or maybe even in physics, there's something called a conversion factor. Well, what's a factor? A factor, if I have A, B equals C, A times B equals C, this A and B are factors, right? And this is the product. So a factor is something that you're going to multiply. So a conversion factor is a number or a group of numbers you're going to multiply. And what you do is you get an equality like this. This is an equality that says 1 coulomb equals 6.25 times 10 to the 18th electrons. Well, I can write it like this as a fraction. 1 coulomb is the same as 6.25 times 10 to the 18th electrons. Or I can write it the other way. I can say, if I have 6.25 times 10 to the 18th electrons, I got 1 coulomb. I can write it as a conversion factor one way, or I can flip it over. And then what you do is you can use that conversion factor to help you cancel units in the right way to solve a problem. So for example, in problem number 2, we have 12.5 times 10 to the 18th electrons, and they're added to a neutral dielectric. Now, I don't know if you know what a dielectric is. You don't even have to know what it is to do the problem. All you need to know is that it's neutral. It's neutral. Just so you know, a dielectric is just another word for insulator. But I have a neutral insulator or neutral dielectric, and I'm going to add to that insulator or dielectric 12.5 times 10 to the 18th electrons. I want to know how many coulombs of charge am I adding? So I will start with the number I want to convert over. So I have 12.5 times 10 to the 18th electrons. And I want to convert it to coulombs. So I'm going to multiply either by this conversion factor or by this conversion factor. Now, the right way to do it is I want the unit of electrons to go away, and I want to end up with units of coulombs. So to do that, I need to multiply by this one. Well, let's say I didn't know that, and I tried to multiply by this one. I would say, all right, I got 6.25 times 10 to the 18th electrons divided by 1 coulomb. Well, see, I can't cancel E with the C. If I want to cancel units or numbers, I got to have something in the numerator and denominator that I can cancel. And since this is in the denominator and this is in the numerator and they're different, I can't cancel. What I want is this one. I want the conversion factor with the E in the denominator, and that's the first one. So this is the wrong one I chose. So what I really want to write is 1 coulomb is the same as 6.25 times 10 to the 18th electrons. And now I know I got the right one because that E right there is going to cancel with that E. Matter of fact, that 10 to the 18th is going to cancel with that one. What I'm really doing is I'm taking 12.5 and I'm dividing it by 6.25. And if I do the math, this is going to equal to what? 2 coulombs. So my charge Q equals 2 coulombs. Now let me pause here because there's one important thing that I want to make sure I got like 4 minutes. There's something very important about what I just did that I want you to understand. When you do math with charge, like we just did, it gives you the correct magnitude of charge, but not the correct sign. Let me say that a second time. When you do math with charge, like we just did, it gives you the correct magnitude of charge, but not the correct sign. You have to supply the sign. What do I mean by that? Well, I know over here when I do the math, I end up with 2 coulombs. But is that 2 coulombs positive or is it negative? How do you know? Is this positive 2 or is it negative 2? Well, the answer is, since the 2 coulombs came from coulombs of electrons, then the charge should be what? Negative. That's important that you understand that. Let me show you something else. I'm going away from the lecture, but I want to make sure I emphasize this. Let's say I have an object that's neutral. So I'm just going to draw this. And let's say I'm going to reach in there and grab up some electrons. So right now, it's neutral. There's no charge, but I'm going to take out 2 coulombs of electrons. So I got over here 2 coulombs of electrons. I'll just put electrons. Well, how many electrons is that? I don't know. It's 2 times this number. That's how many electrons I took out. So over here I have 2 coulombs of electrons, and if they're all electrons, then this charge has to be what? Negative. But what about, now listen, it was neutral at first. I removed 2 coulombs of electrons, so now I charge this too. I transform electrons from here to here, which means this area here is charged at negative 2 coulombs, but now the charge over here is what?
Positive.
Positive.
Positive 2 coulombs. See what I'm saying? So you got to be careful. You got to watch those signs. Let's say that you walk into the room and all you knew was this had a charge of plus 7 coulombs. So you walk into the room, you don't know what this thing is, but whatever it is, it has a charge of plus 7 coulombs. And then what I'm going to do is I'm going to add these electrons to this object. Once I add the electron to this object, what's the new charge?
5.
It's going to be 5. I got minus 2 coulombs. I'm adding. So the new charge is 5, positive 5. So you got to be careful when you're dealing with coulombs and kind of watch the physical situation. You got to know when to put a plus sign, when to put a minus sign. So you just got to think about that. And one last thing, I got 1 minute. I want to show you this before you sign off. Goes back to charge. Q means quantity of charge. But when I use Q for a symbol, I can use a capital Q, I can use a lowercase q. In either case, the unit will be a coulomb. So the question is, when do I use a uppercase Q to represent charge, and when do I use a lowercase q to represent charge? Well, here's the answer. If I'm dealing with a single charge called a point charge, I'm dealing with a single charge, like maybe here's a charge here, and here's a charge here. These are what we call point charges. So that's a single charge, maybe a single proton or a single electron. That's a single charge, single proton or a single electron. Then it's proper to use the lowercase q. So I might call this charge Q1. I might call this charge Q2. If I'm dealing with a group of charges, and most of the time, you hardly ever deal with one electron or one proton. That's silly. But you can think about that in physics, having a point charge. Normally, we use a bunch of charges together. So if I'm dealing with a group of charge, that's when I use the big Q. So if I had a bunch of charge together in this area, I will call it capital Q. Now, I'm being really picky. I don't care. I really don't care if you use an uppercase Q or a lowercase q. I don't care, as long as you get the right answer. But strictly speaking, in physics, this uppercase is telling you one thing, and the lowercase is telling you something else. The uppercase Q is saying, hey, I got a bunch of charge, I got a group of charge, and the lowercase says I have a point charge. I have a single electron or a single proton, and I'm talking about single point charges. Well, I went over, guys. I'm sorry, I ran out of gas again. Not gas, but I ran out of time. So, does anybody have any questions for me before we sign off?
Yes, I do. So, can you pause this video?
Yeah.
I want to learn more.
I'm laughing because, is it Riley? Is that Riley?
I want to
Yeah.
learn more.
I'm laughing because Riley and I think we talked on the phone or last night or maybe.
Yes, sir.
And I had to post the video for it. So yeah, that's no problem. I'll do that for you.
Cool.
I'll
Thank
get
you.
those right away. And because if you're in all fairness, I record these videos in section 002. So if you're in section 002, you have instant access to the video as soon as Blackboard finishes processing. Like when I turn the camera off, about an hour later, the video is available to you. But Riley's in 001, so he can't get the videos until I put them up on YouTube. So he said, hey, can you go ahead and get this video up so I can go ahead and watch it and study it? I'll do that. That's no problem.
Thank you.
Any other questions or comments?
Were
Yeah,
you
would you
still
mind?
going to, sorry, we're still going to upload the textbook, copy of the textbook?
I didn't give you a link to the textbook.
Did you put it in on the course page? I haven't got it.
Okay, I don't know, but I'll tell you what. I'll do that as soon as I sign off. I'll just post it as an announcement, a link to the. Now it's the 9th edition, but it's okay because you guys are on the 10th edition.
Okay.
I'll post that link to Blackboard. You can just click on it and you can go to the 9th edition of the textbook. And guys, if you don't have your book, please use the link because you got to read this material. Don't just come and listen to me talk and do problems. If you do that, you're going to miss out because I talk about probably 90% of the stuff in the chapter, but you got to read the other 10%. So just read the whole chapter. So yeah, I'll put that link up here in about 10 minutes. I'll put it up as an announcement. You can click on it. It'll take you right to the textbook.
All right, thank you.
Okay, and there was somebody else had a question?
Yeah, I was just wondering if you could go back through that, the equation for breaking down the shell capacity.
Yeah. Yep. I can do that. So you want the equation, or tell me, the equation was,
Well, yeah, the equation was SC equals, and is it 2 times n squared?
yep, that's it.
Okay,
So we had that, and then to know that, you gotta know the shell numbers, right? To get the shell capacity, you
right,
gotta have the shell letters. So we had K, L, M, N.
Yep.
You gotta know that K is the first shell, L is the second, M is the third, N is the fourth shell. So that's this. That's the N. That's this.
okay,
That's the N. So then all you gotta do is put each of these in the equation. So for the K shell, SC is gonna equal 2, K is a 1, so that N is a 1 squared. And that's where I got 1 squared is 1 times 2, that gives me a 2. And then for L, SC is 2 times that number squared, 2 squared, that's a 4, 2 times 4 is 8. And then M, SC is 2 times 3 squared. 3 squared is 9, that gives me 18. And the last one is N, gonna be 2 times 4 squared. 4 right there, squared.
okay,
2 times 16 is 32. That's where we got those numbers from. So that's the
Okay.
shell capacity. Yep, that's where those came from.
all right.
Good question. Anybody else? Okay. Well, guys, I guess that's it for today. I didn't get as far as I wanted to, but I get sidetracked with this physics stuff, and it makes me not get to where I want to be. But that's okay. That's all cool stuff. So, guys, have a great weekend. No, wait a minute. It's not Friday. I'm ready. I want to fast forward to Friday already. Have a great rest of the week, and I'll see you on Friday. And I'll post the link to the book now. And Riley, I'm about to download that video and get it up on YouTube for you.
All right, for like the chapters, is one lecture like one chapter, or
No.
how much reading do we have?
1 week, I give you a week of material. So 1 week is 1 chapter. But I'm gonna tell you now, we probably won't finish this by Friday. We'll probably go. We'll go on to next week, because chapter 2, I go into so much detail. I always kind of, So this will go on. We'll probably use Friday and Monday. So you'll have more time. You'll have plenty of time.
Sounds good. Thank you.
All right, guys. Have a great one.
See ya.
Thank you.
You
See
too,
later.
thanks.